Okay, this is blood donation behavior prediction demonstration in which we are going to predict the behavior of a person that on the next ask if he or she is going to donate blood or not. So what are the objectives of this demonstration? In this, we are going to use the machine learning application in healthcare, like blood donation is somehow related to the healthcare, and based on historical data predict who is going to donate blood on next ask. And in this I will show you how to use the stratified sampling and what is the impact of using this, and I will also show the how to deal with the imbalanced data, because the data on which we are going to work is imbalanced. And we will also see the factors affecting blood donation decision by using the variable importance. The dataset for this demonstration is open dataset, and it is available on both Azure machine learning repository and on UCI machine learning repository. The data link is this one, and this link will be provided in the description section of this demonstration. Okay, so come to the data set part. This is the data set link on the UCI machine learning repository, where you can find some description on the dataset. This is a well-known dataset, and this dataset was basically published or belongs to the date 2008 in this one. And the idea of this is to do the task of classification. And there isn't any missing values. There are 5 attributes, and likewise there are 748 examples, and this is a multivariate dataset. So whenever you come to the UCI repository, you see a summary of the underlying dataset like in this format, and this is very useful and well known among the machine learning community. Here is the information on dataset. You can see that they basically they have a blood transfusion service center in the city in Taiwan, and they go to some university places and ask for the blood donation, and they go after every 3 months, and once they have selected 748 donors at random from the donor databases, and they have labeled these information like among those 748 who provided the blood or who did not. So here is the variable description. There were 5 attributes we have seen. The first one is the recency. It means the months since last donation, and the frequency, total number of donation that person have already given. And this is the monetary, that is total blood donated in number of cc, and this is the time, month since first donation. So and the last one will be a label or the outcome, and that will be a binary variable representing whether she donated blood in March 2007. So basically, based on the information that they collected on the March 2007, this is the behavior of the people that was on March 2007 blood donation activity. They received the information that like some people donated and some not donated. So based on this data, the goal is to predict for the next in the next round, that will be after 3 months, whether what factor will be affecting the blood donation behavior. So let's start prediction on this, and by using the machine learning. And first we will go to the Azure machine learning portal, and we assume that you have already set up your Azure machine learning account. Now we will go to create a new machine learning experiment. Click on new, and you will see the experiment section here. Click on this blank experiment, and you can give any title to this, like blood donation prediction. Now I have the dataset in Azure Machine Learning, as well as I have the data set over here. So I have both the option. If I want to import the data from machine learning from here, then I can go to this data folder, and inside that data folder, this is the transfusion.data. This is basically the data set, and I can import this in my Azure Machine Learning, or can directly import the information from the samples section of the Azure Machine Learning. So I would prefer to directly import this. Here in this data set, if I want to see that what is inside, then click on visualize to see the exploratory analysis of this data set. As we have seen that there were 5 columns, these are 5 columns, and the rows are the same. And the first one is recency, frequency, monetary, time, and class. And we can also see the distribution of the data in this right side panel, and this for this one, and for this one. So we can clearly see from the output class that people who did not donate the blood are more, like 570, and people who donated are among 178. So only 24% donated their blood among the whole population. So this is clearly not a balanced data set, because one class is very dominant number of rows and the other class is not as much. So this is the data set that can be called as a imbalanced, not too much imbalanced, because in some cases we can also see like 5% information of the other class. So this is imbalanced but not too much imbalanced. But it's true that this is imbalanced, because normally we expect the two classes, it should be good, like one should be 60, the other should be the 40 or something like that. So there should not be a greater difference between two classes. Okay, now first thing I want to see that whether there is missing values or something like that, or what is the summary. So I will summarize from the statistical function this data set. To summarize, just take this and run this summarized data model. This will basically create the aggregation of the data and provide some information like this. Click on visualize and see what is inside. We can see for the recency feature there are 748, and for all 748, and the unique count or the unique values are this much, and there isn't any missing value in recency, not the rest of the other columns. So we have a very clean and good data set, and we don't need to do any missing value treatment in this. And we can also see the maximum, minimum, first quartile and range quartile. We can also see the monetary feature has a different scale than the other features. This other features has minimum, maximum in between 0 to 74 and 50, likewise 90. But for this feature we can see this minimum maximum value is on a different scale. So ideally we should scale in this scenario, we should scale or normalize the feature, but in this demonstration we are not going, because this is a very simple demonstration. We are not going to normalize right now, but yes, it is ideal to normalize the data set in such cases to create a very smooth machine learning application. Now in the next step, we have seen the data set. In the next step I will split the data set and then try to implement the machine learning model. So here is the split data, and I will join this to normally people use 70 to 30% split or 80 to 20% split. I am going to splitting 80 to 20. So 80% will be for the training and 20% will be for the testing. So here we will see that what happens if I select the stratified split option or if I don't select. So first I am going to not selecting the stratified split. So quickly run it and see the output, and inside output we will see the distribution of data set, that the distribution of the two classes. Okay, the output will always in two nodes. Like the first node will be the data set for the 80% of the data, and the other will be the rest 20% rows, and this all is coming as randomly. Okay, if I click on the 80%, that is for the training purpose, and click on the class, so here we see the 76% for the class 0 and 24% for the other class. And here I can also see in the test what is the representation, 78 and 22. So we can see the representation of two classes are different in training and testing, while we can also see the actual distribution of these two classes in the data is basically 76 and 24. So this is close to the training, but the testing data set is not close. So what I want is stratified split true, and here I will provide the output column. Output column will be the class, and this will, I can also provide here some random seed to regenerate the same result every time. Now if I run this, then I am expecting to see the same distribution of the classes in both training and testing, that is in 80% or in the 20%. Here is the 76% and 24%, that is the first class, and this is the second class. Now see the inside the test data set, the distribution should be similar, 76 and 24. Okay, so now what we have done, we have created two data set, one for the training, other one for the testing, and in both these two data set the representation of the classes are same. If we don't apply the stratified sampling, it is quite possible to take the number of minority class in very less number in the testing class, and this sometimes creates difficulty in the evaluation and does not provide a very good evaluation for the modeling. Okay, so the other thing is, we have seen this is imbalanced data set. Therefore, to overcome this imbalance problem, we have a smooth option. And what is this? Basically synthetic minority oversampling. This basically increases the number of classes of the minority class. Number of rows in our case is less, so so there is an option what I can do, whether I can apply the smart before splitting the data set, or I can apply the smart after. So now I will prefer this smart option on training data set only, not on the test data set, because by using the smart option I am going to synthesize or modify our training data set, and I don't want to modify the real data set, the test data set, which should be original. So I want to test my machine learning model on completely original data set that has not been treated by any way. So here I have provided this mode after the splitting data set only on training data set. This percentage is 100%. It means this will increase the number of rows to 100% for the minority class. I am going to apply the 100% right now and see what is. So first quickly see the number of rows before the smooth, the number of rows is almost 142. Okay, now run this mode, and after this we can see what will be the number of rows while it's running. Okay, see, this is the error. So what is this error? This error is showing that I have not specified the label column. So based on where this should find the classes in which column, so I will provide the class column here. So this variable has two values, 0 and 1. So run it again and see the output. So it's more take two major input. One is the percentage and second is the label column. Now see the output. Inside this column we can see some increased number of bar for this. There is 248, almost double, and this is 38% and this is 62%. I can even now improve the size by providing some other value like 150 or say the 200 to make it more balanced or more like the prominent class. Okay, now you can see what is the result again. Here is, see, after 200% of that class there is a almost 426%, 48% here and 52%. So this is very ideal, although we have synthesized and created. But if you find a data set with such level of distribution, then you are very lucky, and the machine learning will have not much hard time in predicting and classifying. Okay, I will move further now to implement the machine learning model. For simplicity, I will start with the logistic regression, and because we have only two class, 0 and 1, then I will use the two class logistic regression. And here I will pick the train model component. Here's the train model, and I will also take the score model, as well as I will also take the evaluate. So this is pretty standard. Whenever you do modeling, you take similar components. So what this take, train model take untrained model. This is the untrained model, and I will drag this to here, and I will, and this is still red. It means it is asking for the output label, and I can provide it the output label that is basically class. Okay, basically why this is red, because I have not provided the input data set. So from where it will come, this is the output of a smooth, this will come from here. Okay, this is fine now. And for the next, this output is train model, this will go to the train model to score, and here I want to score not on my training data set but on my testing data set that will come from the second node of the split data. And this is to evaluate the model, and it only takes the score data set, and I will join this score data set with the scored data set, and I will take the all parameters as a default, and quickly want to run this to see the output of this. So there are not much number of rows, it should not take much time while training. It's training inside. Why this happened? Because of any spelling mistake. So I have selected this class as a with C, small c. Now I will provide the right. So remember, this train model should also be properly provided the class that we are going to predict. Okay, Running again. It's running while on the train model. Has completed the train model, is scoring the model based on the training, and it's scoring on the test data set. And remember, the test data set is the original one. We have not synthesized and have not added anything inside that. We can see the output of this code model first. Here is the output of this code model. Inside this code model, we have this is code label 0, 1, and this is code probability, and apparently there are some right predictions, like the original class in actual class label was 1 and predicted as 1, but here it was 0 predicted as 1. So we can see very high number of differences in the classification. So these are the misclassified labels, and likewise. So let's see what is the evaluation, what is the accuracy of this model. Okay, overall this is not a bad model, but not very strong model, because you can see the precision is very low. Recall is good, although accuracy is 68%, and the F1 score is almost 50% to 0.50. AUC is although looking good, 0.712, but we know the precision is not as good, and we have seen the false positive number is high. But now I want to compare that I have applied this mode. Okay, if not apply this mode, what happen? So to see the difference, I will train another logistic regression model here, and this time I will provide the output of the split data, not the output of the smooth after applying the synthesization. And this is, and the logistic regression model should be here. This one. This will take model, and this will take the data, and this also should be joined with the output of the test data. So this is again the classification, but on the regression, but this time I am not providing the smooth technique, and let's see the output of this. So normally smooth increases the accuracy of any model here. So we have seen the accuracy of the previous one. Now if you go to here, and if you go to see the accuracy, see the precision is very high, but the recall is very low, 0.028, and the this confusion matrix is also providing some information that how it is going. False negative is very high. AUC is 0.71. So overall this is biased towards the prominent class. So this is not a very good machine learning model. Okay, now one thing more. If I want to see the output of these two models side by side, how can I see? It is possible by using by providing a very simple R script. Here is quickly R script for this, and I will remove this from here. I will align the okay, I should not have remove the evaluate. There should be the evaluate to take the output from here, and the script here. So what I'm going to do, I'm adding a new column in the output of this evaluation model. And to do this, I will go to the execute script. Inside that there are two data set, 1 and 2. I have only provided the 1, so I will remove this second one to avoid any error, and I will also remove this plot part from this. And here I'm not going to bind the data set, but basically I'm going to assign this, because this data set will be the output of this. Now I will add a new column in the data set 1, which will be the classifier, and for the first one I will write the with smooth. Okay, so now just run this and see the output of this. After running has been completed, we can see the result of this R script. The result of our script has the other columns as well as the classifier column with this label with smooth data. So I will quickly copy this and put it here, and we'll link it with this. We'll go and type without a smooth technique, and I want to see the result of these two side by side. So the best way is to add the rows, and the result of this should be added. Now run this and see the output side by side to compare the result of a smooth and without a smooth. While it's running, executing the script, and now combining the rows into one. Here I can see the visualize, and now I can see the output of these two. The F1 score is very good for with smooth applied. AUC is almost nearby, but the recall 0.6, 60% is recall and 40% is the precision. So we can see a balanced precision recall and F1 score with the smooth, but without smooth these information are different. Although if we only see the AUC, we will not have the right idea, and if we only go with the accuracy, we will not have the right idea that what is going on. So it is very important to see the precision and recall to compare the model accuracy. And again, we have evaluated this on the data set that was original. If we go and evaluate this model score and evaluate this model on the output of this smooth, then we can find a different result as well. So but in my opinion, it is better to apply the smooth after splitting the data and keep the testing data set original. Now we will see the variable importance. To see this, just drag the permutation feature importance here, and we would like to see this variable importance in the data that was smooth. Okay, here is what are the two inputs? Train model. So we will see the train model from here, put it here, and it asks for the test data, and we know we have the test data here. Put it here and make it here, and just run this. It has been completed now. So see the output of the permutation feature importance. You can see the recency as most important feature, then the time and the frequency monitoring has almost less impact on this. So this recency and time are the two more important factors that are predicting the machine learning model. Here is one important thing. Before applying any machine learning model, we have an option to see the variables or features that has the more predictive powers. So for this, go to the feature engineering section. Inside the feature selection section, here we have filter based feature selection, so you can see that which features are most important to select. And here can and what it's asking for the feature scoring method, whether I can provide the Pearson correlation or something else. But here I'm going with the Pearson correlation and asking for the target column. So I will provide a target column, which we know is the class, and when we will run it, you can see the output. And in output, we should expect the features that have more correlation or predictive power with the output label. Here we will find the resultant, the filtered data set. We only see the recency is important here, and here we can see the correlation of each feature with the class. So we can also decide before modeling by using this feature correlation by filtering the feature, or we can also use after training by computing this feature computation, that which features are more important in our machine learning modeling. So he can see the recency is here, the most important, and in the filter based feature selection, the recency was the only powerful and it has a more correlation. Okay, thank you very much for watching this video.